Hi everyone, I'm Varsha Bhatt, and through this talk I'll be discussing the highlights of the paper titled Identifying Influential Spreaders in a Social Network While Preserving Privacy. Let's begin by understanding the motivation for the work. We often encounter situations where we are required to investigate the spreading phenomena prevalent in a system consisting of a set of individuals. For example, it could be the spread of diseases within a population or the spread of information or rumors through word of mouth, etc. An approach often used as a solution to address these problems is to model the interactions among the members of the population as a social network and thereby study the properties of the emergent network. Thus, social network analysis is the broad umbrella that encompasses the common set of tools and techniques that have been developed to study the structural properties of the graph representing a social network. Each entity of the system is represented by a node in the graph, and the interaction between two entities is captured by an edge between the corresponding set of nodes. Most of the tools and techniques designed to perform social network analysis assume that the entire graph representing the social network is available as input, using which the desired network analysis can be easily performed. However, the motivation for the current work stresses on scenarios where the network is not known in its entirety and is rather present in a distributed setting. That is, rather than the network data being housed in a central repository, we focus on scenarios where it is distributedly owned by multiple data owners in such a way that each data owner sees only a partial view of the entire network. The union of all the views of the data owners captures the network in its entirety. It's also important to note that each data owner considers his share of the network data to be private and refuses to disclose it in public. Under this setting, the problem we focus on is to identify influential nodes with respect to the overall network. This is an important problem to be addressed when introducing targeted interventions in the spread of diseases, to achieve efficient advertising strategies, and in general to identify key players in a system. Traditionally, the problem has been addressed in the trusted third party model, wherein each data owner discloses his share of the private data to a third party who is mutually agreed upon by all of them. The third party is trusted not to disclose their information. Having obtained the private data from all the data owners, the third party ranks the nodes in the network using some of the standard ranking techniques such as K-shell decomposition, page rank, and vote rank centrality measures. He then the first and foremost being that the trusted third party ends up learning the complete picture of the underlying network, which makes it difficult to find it by all and often ends up being a costly affair. Thus, we propose the use of secure multi-party computation or MPC to design secure variants of these standard techniques. MPC is a branch of cryptography that allows the parties to communicate among themselves to securely compute the output of a predetermined function, let's say f, which takes as input the private data of each of them. That is, the computation ensures that the parties learn no additional information apart from the desired output. More specifically, the current problem can be modeled as an instance of MPC as follows. The private input here would be the subset of edges that each data owner is aware of. We note that the set of all nodes in the graph is assumed to be public. It is the presence or absence of an edge that is regarded as private data. The global function f that the data owners are interested to learn is modeled to output the rank of the nodes in the network. We then consider a two-party setting where each of the data owners distributes shares of their private data to the two computing parties in such a way that the individual share does not leak any information. The two parties, let's say P1 and P2, evaluate the function f securely, and the computed output is communicated back to the data owners. We assume that the two parties do not collude with one another, and therefore we are dealing with semi-honest adversarial model only. Under this setting, we first consider the problem of securely performing K-shell decomposition. This method of ranking nodes was first formalized by Borgatti and Everett, where the idea was to decompose a given graph iteratively by categorizing nodes into shells. The main objective was to identify the innermost shell nodes, referred to as the core nodes, that are known to be the most influential nodes in the network. The traditional algorithm would proceed as follows. We begin by considering the entire network and start pruning all the nodes that have degree 1 or less. All such nodes are assigned shell value 1. Note that the pruning of nodes may result in the degree reduction of other nodes as well. Hence, the pruning process continues until there are no more nodes left having degree 1 or less, and all such pruned nodes are assigned shell value 1. In the second iteration, we consider the remaining nodes, which are shown in green here. We prune all the nodes that have degree 2 or lesser and continue the pruning process until there are no more nodes having degree 2 or less. All such pruned nodes are assigned shell value 2. And this way, the process iteratively prunes nodes in the network, and it continues until there are no more nodes left in the graph. The nodes identified in the innermost shell, which is the core nodes, are thus determined. The pseudocode for the process is given here. The outer for loop determines the shell value currently being assigned, and the inner while loop determines the nodes that are pruned and assigned the current shell. Clearly, we observe that the algorithm does not qualify to be data oblivious. This is because an algorithm is said to be data oblivious if the execution of its instructions and the memory accesses made during its run are independent of the input. Clearly, we note that the execution of the instructions in the K-shell algorithm can leak sensitive information such as the number of shells that the graph is decomposed into, the nodes pruned in each iteration, essentially the same as the number of nodes assigned to a shell, and also the nodes whose degree is updated in each iteration depends on the input graph structure. As a solution to this, we design data oblivious equivalent of the algorithm and translate the same into a secure protocol. In order to do this, we resort to the RAM model of secure computation, which considers the oblivious RAM primitive first introduced by Goldreich and Ostrowski. The ORAM primitive allows oblivious accesses to memory locations in sublinear time, which is far better than the linear time incurred by the circuit model of computation. Thus, the RAM model of secure computation, RAM-SC, allows us to have the best of both worlds by combining the ORAM primitive and the circuit model of computation. There are several schemes that are designed specific for this, such as the circuit ORAM and the square root ORAM. In order to make the most of the RAM model of secure computation, as well as to account for the sparsity of real-world networks, we use a space-efficient alternative to the adjacency matrix representation known as the edge list representation. It consists of two lists E and IDX. Assuming that the nodes in the graph are labeled 1 to n, the list E stores all the neighbors of node 1 followed by the neighbors of node 2 and so on. The list IDX, basically a list of indices, stores indices to E that acts as a delimiter to the list of neighbors of each node. Thus, unlike in the case of the adjacency matrix representation, the length of the list E also reveals the number of edges in the graph, not just the number of nodes. Using the edge list representation, we design a secure protocol for performing K-shell decomposition. The key aspects of the protocol are highlighted as follows. We first obliviously sort the vertices in the graph based on their degree and store it in an ORAM array called vert. This is also maintained as an invariant throughout the protocol, which allows us to prune nodes based on the ordering of the nodes according to the array. Secondly, we modify the looping construct to avoid an input dependent number of nodes being pruned in each iteration. Rather, in the modified for loop, each iteration either obliviously updates the next node to be pruned or processes a neighbor of the current node. Thus, the for loop runs through order v plus e number of iterations. Within the for loop, we utilize the oblivious if-else construct to achieve the switch between pruning of a node and processing of its neighbor. Additionally, unlike in the traditional algorithm, here we would require to explicitly maintain the shell value that is being assigned. The asymptotic complexity can be determined as follows. There are various oblivious sorting techniques explored in the literature. Assuming the sorting techniques such as the batch or odd even sort, the associated complexity would be order v log square v. And in the main for loop, in each iteration, we are essentially performing a constant number of ORAM accesses. Since this is repeated over v plus e number of iterations, the complexity would be order v plus e times the overhead of performing ORAM access. Note that the complexity in the RAM model depends on how the ORAM primitive is instantiated. Here we compare between the square root ORAM and the linear scan ORAM. We also compare our protocol to a previously proposed protocol that is designed in the circuit model using the adjacency matrix representation. We note that the current protocol using the edge list representation fares better than the previously designed protocol. We also have implemented the protocols in the secure framework of obliv-C, which is a C language based framework that relies on garbled circuits at the backend. The concrete runtimes for the protocols tallies with the asymptotic complexities derived earlier, and clearly the protocol for the edgeless representation in the RAM model of secure computation fares better than the adjacency matrix variant designed purely in the circuit model. Next, we consider the secure variant of the PageRank centrality. This centrality measure was first introduced by Larry Page and others as a method to rank web pages. Here, the notion of importance of a node is associated to the quality of its inlinks. I'll briefly discuss the random walk method that is traditionally used to compute the centrality value. The idea is to take a random walk on the given graph while keeping track of the number of times a given node is visited. We begin the walk by picking a node uniformly at random and incrementing its visit count value. Let's say node 1 was picked. We then toss a coin at each step to determine the next node we will be visiting. In case the coin toss results in a head, we continue the walk by choosing a random neighbor of the current node, highlighted in green. Let's say node 5 was picked. In case the coin toss results in a tail, we continue the walk by choosing any of the nodes in the graph at random. Hence, all nodes become candidate nodes for the next pick. And this process continues on for a predetermined number of times. Clearly, the instructions executed in each step of the algorithm depends on the structure of the input graph as well as on the result of the coin toss. Hence, the algorithm again fails to qualify as a data oblivious algorithm. We therefore resort to the iterative approach to computing PageRank centrality, which proceeds as follows. All the nodes begin with an equal PageRank value, let's say 1. Then, in each iteration, we consider every node to distribute a fraction of its PageRank value equally among its neighbors through the outgoing link. And then the remaining PageRank value is contributed to a common pool. At the end of the iteration, the total PageRank value collected in the pool is equally distributed among all the nodes. Therefore, the new PageRank value of each node received through its inlinks and from the pool is updated. In the second iteration, the same process of redistributing the PageRank values is repeated. However, we consider the updated PageRank value this time. And this process of redistributing PageRank values and computing the updated PageRank value continues for a predetermined number of times. The key ideas of the protocol to compute PageRank using the edgeless representation are as follows. All the arrays with data-dependent memory accesses are stored as ORAM arrays, such as the edgeless, degree, and the PageRank values. The number of iterations of the PageRank updates needs to be predetermined and fixed. We also modify the looping construct, and the protocol essentially consists of two main loops. The first is used to scan over the edge list to compute the redistribution through the outgoing links, while the second loop is used to update the PageRank value with the contribution from the pool. And as we scan through the edge list, we are either updating the next node to be explored, or we are accounting for the contribution of the current node to one of its neighbors. This is obliviously done using the oblivious if-else construct again. And as we scan through the edge list, we also need to explicitly handle the case of encountering a node that has no outgoing links. The asymptotic complexity of the protocol is as shown. A constant number of ORAM accesses is performed over order v plus e iterations in the first nested for loop and over order v iterations in the second. This entire process is repeated L times, where L is the number of times the PageRank update is performed. The asymptotic complexity for the specific case of square root ORAM and linear scan is as shown. And again, this outperforms the previous approach based on the random walk method using the adjacency matrix representation. The concrete runtime of the protocols also shows the same. We note here that the number of iterations required in our approach is much lesser than the length of the random walk required in the adjacency matrix representation. Lastly, we consider the vote rank centrality measure. This idea is similar to PageRank in the sense that each node vouches for the importance of its neighbor by voting for it. Thus, the score of each node is the sum total of the votes that it receives. This centrality measure was introduced by Zhang et al., where the focus was on just the local neighborhood of the node. The motivation for this specific centrality was to minimize the overlap in the sphere of influence among the top picked nodes. Let's see an example of how to compute vote rank centrality. All the nodes have two attributes, VA denoting the voting ability of each node and the score. The voting ability is set to 1 and denotes the value of each vote contributed by the node, and the score is initially set to 0. All the nodes vote for their neighbors in such a way that the score of each node is equal to the sum total of the votes it receives on its incoming links. The node with the highest score is picked as the most influential node in this iteration. In order to reduce the probability of picking the next most influential node from the same neighborhood, we reduce the voting ability of those nodes that have voted for the highest scoring node in the current iteration. This process continues on for k steps if we wish to determine the k most influential nodes in the network. We propose two secure variants, the first based on the adjacency matrix representation designed in the circuit model, and the second based on the edgeless representation designed in the RAM model of secure computation. So the first approach, using the adjacency matrix representation, requires us to maintain two private arrays, one to maintain the score and the other to maintain the voting ability of each node. In each iteration of the algorithm, we perform the following operations. The score of each node can be easily computed by scanning over the adjacency matrix column-wise and performing a secure addition. We then scan through the score array to obliviously determine the highest scoring node and reset its voting ability. We also reveal the identity of the highest scoring node. Given the identity of the highest scoring node is revealed, we can scan through the entries of the column corresponding to this node to determine its neighbors whose voting ability needs to be updated, and then we reset the scores of all the nodes in preparation for the next iteration. The overall complexity is k times v square, since we are essentially scanning through the adjacency matrix k times. In the second approach, we use the edgeless representation, which is a little trickier. We require to maintain an additional data structure to ensure that the top ranked node does not end up being picked again and again, which was easily taken care of in the adjacency matrix representation. The following steps are executed k times. In each iteration, we essentially perform two scans over the edge list. The first scan, we iterate over order v plus e number of times, such that in each iteration, we are processing either the current node by accounting for its vote to its neighbor, or we are updating to the next node to be processed. A similar second pass is required to update the voting ability of some of the nodes. Hence, the overall complexity is as given here. Each pass consists of order v plus e iterations of some constant number of ORAM accesses. This is repeated over k times to pick the k most influential nodes. The asymptotic complexity of both the variants is as shown here. We note that the adjacency matrix representation outperforms the edgeless representation for only the considered graph sizes here. This is because the break-even point occurs at a much later stage. Thus, we saw the need for analyzing distributed sensitive social networks and the applicability of MPC as a solution to performing social network analysis in a privacy-preserving manner. We saw the secure variants of three popularly used ranking methods and saw the advantages of using the edgeless representation in comparison to the adjacency matrix representation. Thank you.